The complete molecular equations, complete ionic equations, and net ionic equations for the acid-base neutralization reactions look super similar to what we saw for the precipitation reactions. The only difference is that during a neutralization reaction, we form water as a product. So the water, it acts the same way as the solid. That's the thing that isn't going to be broken down in any of the different equation types. Let me show you what I mean. So here we have hydrobromic acid, and I'm going to split that into its ions. Sodium hydroxide, also split it into its ions. And we're going to predict the products by do-si-doing the ions. So H plus with OH and the sodium with the bromide. H plus and OH. That's going to give us water, H2O. Because we have an Arrhenius acid, a proton, with an Arrhenius base, something that produces OH minus. Those two will combine to neutralize each other and form water. And then the rest of the stuff, Na plus and Br minus, that'll form sodium bromide, which is aqueous. Always check the solubility of the other product. Your water is always going to be labeled as a liquid, but the salt, whatever results from the other two ions, could potentially be a solid or aqueous. Check your solubility rules. So for our complete molecular equation, we have HBr, aqueous, hydrobromic acid, plus aqueous sodium hydroxide, NaOH, forms liquid water, and aqueous sodium bromide. Next, we have our complete ionic equation. And we're going to approach that the same way. If it's aqueous, break it up. If it's liquid, leave it alone. Those two things connected, they're together now for life. And actually, the water will stay together as a liquid until any kind of electric current is applied. So it takes a lot to break those apart. Keep them together. So we're going to do H plus aqueous and Br minus aqueous for the hydrobromic acid. And then for the sodium hydroxide, we have Na plus aqueous plus OH minus aqueous. On our product side, we have the liquid water, and I'll break this one up. So Na plus aqueous and Br minus aqueous. Identify your spectator ions. So we got bromide, exactly the same on both sides. That's definitely a spectator. And same thing with the sodium ion. So at the end of the day, our net ionic equation for this acid-base neutralization reaction is going to be H plus aqueous plus OH minus aqueous goes to liquid water. I'll tell you how to cheat. The net ionic equation is always the same. You're going to see a pattern. If you're mixing an Arrhenius acid, something that produces H plus, with an Arrhenius base, something that produces OH minus, this will always be your net ionic equation. So if you have a multiple choice question and they just ask you for the net ionic equation when an Arrhenius and acid and Arrhenius base are mixed, then you can just jump right to this. We already know what it's going to look like. In this problem, we're asked to consider the combination of phosphoric acid and potassium hydroxide. So for the phosphoric, I remember that 8 goes to ic when you're naming your acids. So phosphoric acid has an anion of phosphate. Since it's an acid, I know it involves H+. Over here with the base, we have potassium and Arrhenius base hydroxide. So for the reagents, I'm going to crisscross the proton, the H+ with the phosphate. That gives me H3PO4. You can assume that all of your acids are aqueous unless indicated otherwise. Potassium hydroxide, here I can apply the solubility rules. Potassium's a group 1, so when it hooks up with the hydroxide, it's still going to be aqueous. We're going to do-si-dome. H+ will combine with OH-, that's going to be the water, the neutralization part of this reaction, and K+ with PO4 3-. This is going to give me K3PO4, which I know is aqueous because of the presence of the group 1 cation. For my complete molecular equation, everybody's crisscrossed in this one. So I'm going to start with H3PO4 and potassium hydroxide. And that's going to form water. And potassium phosphate. What I've noticed over the years is students struggle a little bit to balance acid-base reactions that are not one-to-one. One of the tricks I encourage students who are struggling to employ is, instead of writing water as H2O, as we all know it is, let's keep it as HOH. Then we can consider the OH- as a unit when we're balancing. So here I have one OH- and here I have one OH-. Here I have 3 hydrogens, and over here I just have 1 hydrogen. So I'm going to have to put a 3 in front of the water. So now I have 3 hydrogens. That looks good. That gives me 3 OHs though. So if I put a 3 out front here, now I have 3 Ks, 3 potassiums, and 3 hydroxides. 3 Ks, 3 potassiums, but that's not a problem because there's 3 potassiums over here, 1 phosphate, and just 1 phosphate. I'm not going to break this one down either. Keep your polyatomics grouped together to make balancing a little bit easier. I'm okay with you keeping HOH because I know where it's coming from. However, when you do present an official answer, it should be written as H2O. So once you get it balanced, then change it to H2O. Let's write our complete ionic equation then. This 3 means that there's 3 protons, 3 hydrogens per every 1 phosphate. This is a triprotic acid. But that 3 needs to come out front. It doesn't stay as a subscript. Label that as aqueous. And we have the aqueous phosphate ion. I'm going to distribute this 3. So that gives me 3 potassiums and 3 hydroxides. The water, since the liquid stays together, maintaining the coefficient of 3. And then this 3 belong to phosphate. There's 3 potassiums. So that needs to go out front. It's not part of the formula of potassium. I think I said phosphate. There's 3 potassiums. And then the phosphate. Alrighty, lots going on with the distribution of the coefficients and moving the subscripts. So just give it a quick visual check that it's balanced, which it looks like it is. And then your next step will be to identify and eliminate the spectator ions for your net ionic equation. So phosphate and potassium are both spectators. And so my net ionic equation is going to be everything that's left. So we have 3H plus, 3OH minus, right there. Don't forget states. Going to form 3 molecules of water. This happens. When you have diprotic acids, you're going to see a series of 2s. When you have triprotic acids, you oftentimes see a series of 3s. Since they're all the same coefficient, we actually can reduce it down. So I'm going to divide each one of these by 3 and report my official final net ionic equation as H plus aqueous plus OH minus aqueous, with the water going to form water with coefficients of 1 out in front of each of the species.